Hi, welcome back. So in this second section, I'm going to be demonstrating overfitting in regression and first steps with R. So, so in the last section, we kind of discussed in general what machine learning is good for, but so how are you going to be able to use machine learning algorithms in practice? So to learn a good prediction function for any of the problems that we described in the previous video, and for any other problems that you encounter in your work, you should first gather a data set that you use to train and test the machine learning algorithm. So typically this is going to be a CSV file with rows for observations and columns for features. And then after that, you need to use k-fold cross-validation to repeatedly divide the observations into train and test sets. And so you'll be using the train set to learn machine learning model parameters, and then using the test set to estimate the prediction error. So that's important in order to get a good idea about which algorithms are best for which problems. And so after that, you should try a variety of different learning algorithms. So in this tutorial, we're only going to be talking about linear models and neural networks, but there's lots of other kinds of machine learning algorithms, such as random forest boosting, support vector machines, and really dozens or hundreds of other techniques. So it's important to try a variety of different ones because you really don't know in advance which one will result in the most accurate predictions for your particular data set. It's really important to try different approaches if you're really interested in getting the maximum prediction accuracy. And so finally, one thing I want to emphasize in this tutorial is that each learning algorithm has different hyperparameters which control complexity or regularization or overfitting. And so typically each of these hyperparameters must be chosen by the user, that means you, and they're chosen by dividing the trained data into subtrain validation sets. And so what's the point of that? So the idea is that the subtrain data will be like kind of directly used by the algorithm to optimize the parameters which are made for making the predictions. And then the validation set will be used to select which of the hyperparameters is best with respect to a held out validation set. So that's a little bit abstract. We'll get to an example pretty quick about that. But that's one of the big ideas of machine learning. So I think it's really important to try to understand model complexity and regularization and overfitting. So I'll be talking about that a little bit in this section. So yeah, a big goal of this section is to demonstrate overfitting, and yeah, I mean the the main goal of supervised machine learning is to get accurate predictions on new, unseen, or held out test data, and so yeah, I mean so any machine learning algorithm is prone to overfit. So overfitting means providing better predictions on the train or subtrain set than on a held out validation or test set. So that's definitely a bad thing. So when we're overfitting, that means that we're only getting good predictions on the training data that we've seen so far, and we're not getting good predictions on the new unseen held out test data that we really want to get good predictions on. So to learn a model which does not overfit, so that's a good thing. We need to first divide our train set into subtrain validation sets. And so, yeah, I'll give you a visual representation of what that looks like in just a sec, but I just wanted to mention first, the code for all the figures in this section is online. So if you click on this link, you can go to my GitHub and you can see the code that I use to generate the figures in this section if you want to follow along in your own R console. So first of all, what I'm showing you here is three different data sets and the three different panels going from left to right. And each one of those panels, what I'm plotting is an output or label y as a function of this input feature x. And so the idea is that in the three different panels, we have three different patterns encoded in the data. So in the first panel, we have kind of a linear trend So in linear association between the output and the input here. So as the x increases, the y does as well. So in the second example pattern, we have this quadratic function which kind of decreases down to around 0 and then starts to increase again. And then in the third example data set and pattern, we see something that looks like a sine wave, kind of, and the idea is that it's kind of going down for a bit, then it's going back up again, it's going back down again. So all of these three data sets are examples of regression problems. So this is a pretty simple problem because there's only one input feature that we're seeing here on the x-axis, and the goal is to, given that one value of x, try to predict the corresponding value of y. And so you can see already that depending on what the data look like, the function that you're going to want to use to make that prediction is different. Like, so for example, in the in the first panel, for low x values, we want to predict low y values. But in the second and third panel, we're going to want to predict higher y values for those low x values, right? So we want to learn different functions depending on the data. And so yeah, I mean, the first thing we want to do before we do any machine learning is do this train test split or subtrain validation split. So what does that mean? So first thing that we do is we're going to do fourfold cross validation. And so in the picture, what I did is I just randomly assigned each one of the data points to one of four folds, which I'm showing you in the different colors here. And so you can see that, it doesn't matter where they are in the picture, they just randomly assigned a number between 1 and 4. And so that's kind of, it's important. The idea is that we're trying to kind of get a random subset of the data every time as a kind of like a representative subset for each one of the folds, so that we'll be able to use any one of them to kind of test the algorithm. So for example, if we hold out test fold number 1 as a test set, well, we get something that looks like this. So in this figure, I'm showing you kind of the same data sets, but here I've divided all of the data points which were fold 1 in the previous picture. I'm going to put them in the bottom half of the panels here, and then all of the other folds I put in the top half of the panel. So this is all the data points that were randomly assigned folds ID 2, 3, or 4. We call that the subtrain set. And then all the data points that were randomly assigned fold ID number 1, we call that the validation set. So the entire data set here, we would call that a training set. And so what we do is we subdivide the training set into these two sets called the subtrain and the validation set. And so if we're talking about test or validation fold number 1, so the split looks like this, where all of the fold ID number 1 is going to be in the validation set, and all of the other folds are going to be in the subtrain set. So why is this important? Well, we'll see in a minute, but the idea is that the algorithm will be directly fitting to the subtrain set, but then we're going to be able to use these validation data as kind of held out samples in order to decide what is the good model complexity or regularization hyperparameter to use for prediction. So how would we implement this kind of split in our code? Well, first of all, let's talk about how to just use R in general. So first of all, machine learning model training evaluation can be done in any programming language that supports vectors and matrices, but I recommend using R because it has so many useful packages, and so typically each different package is for a different machine learning model or algorithm, and there's like literally thousands of these things. So you have enormous amount of power at your fingertips when you're using R. So you can download the main R distribution at cloud.rproject.org, and and then we can talk about what is the interface that you should use for interacting with R. And so um, I'm a fan of Emacs. If you're already using Emacs, this is a classical text editor. I recommend that you use R inside of Emacs Statistics. This is a really great interactive development environment, or IDE, for R. You can download that at ess.rproject.org, and you can also see my screencast about ESS here. I've got a YouTube playlist that shows how to use ESS. But so if you don't know anything about Emacs, I don't want to make you learn that, but I mean, it is a good idea to learn one of the two main editors if you're going to be doing any serious programming. But if you don't know already, I think for the purposes of this tutorial, I would recommend using RStudio. So it's another popular IDE for R. You can download that at rstudio.com here. And so once you have that installed, we have to think about how do we get our data into R for doing this machine learning analysis. So typically data sets that we find are in CSV data tables, and in CSV data tables we have one row for each observation, one column for the output label Y variable, and so in regression the label is a real number, and then classification of the label would be a class or category. So in these problems we're talking about a regression problem, so our output Y variable is going to be a real number like we see here. And so the other columns should be inputs, features X that will be used to predict the corresponding output label Y. So in this example that we've seen before, there's only going to be one column with the X variable here, because we're just using one input to predict the corresponding output Y. And so here I give an example with a link to that data set that we used to make the linear pattern in the previous figure here. And so how do we get a data set like that into R? Well, what we can do is we can download a copy of the GitHub repo to get a copy of all of these data sets. And so here's a link to the zip of the current master of that GitHub repository. So after you've downloaded that, you can set the working directory to that that unzipped repository. And then, so here you can use git working directory to make sure that you're in that right directory when you're running this code. And then after that, all of these simulated data sets that we've seen in the previous figure, you see there's a linear, quadratic, and sine pattern. Well, there's corresponding CSV files with those names as well. So if you do sys.glob data star.csv, what that means is to get a character vector of all of the corresponding files that match this pattern, where the star can be anything. And so that's going to save it in this. So this is the assignment operator in R. So this left arrow means to assign the result of this function called to this CSV variable here. And here we're printing out the value of that variable. And so we can see that there's these three data files corresponding to those three data sets that we saw in the previous figure. And so what we can do then is we can read each CSV data file into R using for loop. And so here we're using this for loop over the CSV files that file names that we saw before. And so the idea is we're using this before the for loop, we're going to initialize this empty list, and this list is going to be populated with all of the different data sets that we're going to be reading in each iteration of the for loop. So in each iteration of the for loop, we're first going to be taking that CSV file name, and we're going to be calling this gsub function, which means to do a character string substitution. So here it says, substitute either the data prefix or the .csv suffix with the empty string. So that's just going to give us the pattern variables of linear, quadratic, or sine. And so then after that, we're going to call data table fread on that CSV file name to get this sim.dt object. And so what this does, this double colon syntax means use the fread function, which is defined in the data table package. And so here I have a note at the bottom here. R has many extension packages like this, and in this tutorial I'll be using this double colon syntax to refer to the functions in these extension packages. And so if you don't have that extension package yet and you try to run this code, it'll say something like data table package not found. And so if you get an error like that, I mean, it's really easy to just install the package so you can get it to work. And so all you have to do is type install that packages and then the name of the package like you see here. So after you do that, that should work. And anyway, so that's reading the CSV file from the file name to a data table data structure in R. And then I'm going to set .seed1 for reproducibility. So in R, there's a pseudo random number generator that, and the randomness is controlled by this seed value. So if we're always calling set seed1, that means in this next call to sample here, where we're randomly assigning the fold ID numbers, then it's not going to be random. It's always going to give the same result, and that's always a good idea for reproducible research. So anyway, so this next line, what we do is we sample. So this inner call rep14 L equals n rows sim.dt. Well, what that means is we're repeating the fold IDs from 1 to 4 as many times as there are rows in this sim.dt object, which is the R representation of that CSV data table. And then after that, we're calling sample to kind of randomly rearrange those fold ID numbers, so randomly assign one of those folds to each observation. And then finally, after that, at the end of our for loop, we're going to be assigning one of the elements of this sim data list object. And so this double square bracket syntax, it means to assign to the element of this list with the name pattern. So it's going to, assign, in R we have, everything can be named, and so here the name of this list element is going to be pattern, and the value of this list element is going to be a data table with this CSV data that we've read, with the pattern value that we've created up here, and with the full values that we created over here. And so finally, at the end of the for loop, what we do is we combine all of that stuff into a single data table using this kind of do call rbind idiom. And so what that does is it combines all those data tables that we stored in the list here into a single tall data table with all of those 3 data sets in the same data table. And so the result of all of that is going to be a data table that looks like this, and where the first column is the pattern. It's going to be one of the 3 pattern values that we saw in the previous figure. The X and the Y columns are going to be those values that we plotted on the X and the Y axes, and then the fold ID numbers are going to be those random numbers that we assigned between 1 and 4. And so to create that figure where we have the subtrain validation split, what I did is I just assume that we have the validation fold equal to 1, and then after that we're going to assign a new column to the data table. So there's a special syntax for that, and so here we have this sim.data data table, and so we use a square bracket colon, then the new column name colon equals syntax, and then the new column value. And so the idea is that here we're using this if-else statement to say, so if the fold column is equal to this validation fold of 1 that we've specified, well then we're going to be assigning it to the validation set, otherwise we assign it to the subtrain set. So that's pretty straightforward, right? So all of the observations that were randomly assigned the fold ID 1, they go into the validation set. All of the other folds go into the subtrain set. So finally, let's start to do some machine learning. So after having separated all of those data points into subtrain and validation sets, what we can do is, here I'm going to run a neural network with one hidden layer and 20 hidden units. So what we're going to be doing is, here I show you some R code where we first define the different values for the maximum number of iterations in this neural network. So that's going to be a hyperparameter that controls how much we're fitting the training data. And then we're going to also define these three different pattern values here. So here I have two for loops, one over all of those possible max iterations values, and another for loop over all of the possible pattern values. And then, so the idea here is that we're going to be doing subsetting first this sim data object to just consider the data of one particular pattern. So we call that the pattern data object here. And then what we're going to be doing is calling this nnet function. So this means use the the nnet function in the nnet package again. And so what we do is, the first argument to this function must be this kind of like formula syntax, where on the left side of the formula, that's the output that we want to predict. That's the y variable. And on the right hand of the formula, those are the inputs that we want to use to make the prediction. And so this tilde divides the left side and the right side, sorry. The second argument is going to be this subtrain data set. So here I'm subsetting just based on the observations which are in the subtrain set. And then, so I get to specify a few hyperparameters of this this learning algorithm. So in the nnet function, there's this size parameter which controls the number of hidden units. So we'll see how that affects the predictions in a minute. But yeah, so this is what's called a hyperparameter of the neural network. So it must be fixed before we train the model, and it will control how much overfitting the model can do. We use this lin out equals true parameter in this function to tell it that we're doing a regression rather than a classification problem. And finally, we do max it equals I, which means that we want to use I as the max number of iterations. And that's going to be another parameter, a hyperparameter that controls how much overfitting that we can do. So let's see what happens when we do that. So so in this picture, what I'm doing is I'm showing you the model that we've learned using just one iteration of this neural network learning algorithm. So in neural networks, we train the model parameters which are used to make the predictions using this algorithm called gradient descent. So here in the figure titles, I'm saying how many gradient descent iterations that we've used so far to train the algorithm. And in the picture, I show you what the model predictions look like with this red line. And so actually the red lines are the same in the top and the bottom panels in each column. But yeah, the only difference is in the top panel. Again, this is the subtrain set, which the algorithm is really using as input. Remember, here we're using the subtrain set directly with this nnet function. So it's really trying to fit those subtrain data that we see in the top panel. Whereas with the validation data, it hasn't really seen this yet. And so we're using this as a kind of way to see how well it's generalizing or predicting on unseen data. So anyway, so after having only done one iteration of gradient descent, we see that none of the predictions look very good with respect to the data, right? So here the red line is too high. Here the red line is just flat, where it should be going down and then up again. And here again, it's way too flat, whereas it should be going down, up, down, right? So as we increase the number of iterations, the machine learning starts to fit the data better, right? So after 10 iterations, we can see that, well, it's fitting the linear pattern and the quadratic pattern pretty good, but the sign pattern is still maybe overestimating in this part of the input space, for example. After we keep going to 100 gradient descent iterations. So at each iteration, it's trying to fit this subtrain data set better and better. What happens is, well, it starts to overfit, right? So what we see is that, here, for example, we see in the quadratic pattern, just due to noise, we have some of the data points which are kind of dipping down, and so the function is kind of dipping down to try to get those data points very good, and then it's dipping back up again. But we can see in the in the validation data that we don't have any data which are doing that, so it's a bit ridiculous that it's doing that. And so, if we keep going to 1,000 iterations or even 10,000 iterations, you can see more and more of this kind of like wiggly function behavior. And so this, when you see the functions that are these learned functions which are varying quite strongly or quite wiggly, so this means that the algorithm is probably overfitting. And this is a bad thing because, for example, let's look at just this linear pattern over here. You can see that at the very end, for some reason or another, it's learning this function which is trying to get as close as it can to these last few data points, and then it starts to go down, and it goes down a lot. And so with respect to the validation data, that's really bad. You can see that there's a validation data point that's up here, but the predictions are going to be way down off the charts over here. So it's going to be a really bad prediction for this last data point. And actually, that's true of many other data points too, right? So you can see it's wiggling up quite a lot here, whereas actually there's a few data points that are just right down here. So, so yeah, that's an example of overfitting. And so we can quantify that. And so here's a figure that quantifies the overfitting. The idea is that here we're plotting the mean squared error. So that's essentially a measure of how close these red prediction lines are to the corresponding data points. So we can measure that mean squared error with respect to either the subtrain set or with respect to validation set. And this is what we do with these two lines here. So the subtrain mean squared error is shown as a black line, and the validation mean squared error is shown as the dashed line. And the idea is that, typically with all of these learning algorithms, you see that the subtrain error is always decreasing as a function of the number of iterations of learning. And so this is what we see here. We see that as we increase the number of iterations, we fit the mean squared error is always going down, so it means we're fitting the subtrain set better and better. However, we see that at a certain point the validation error starts going up, and so this is the point after which we start overfitting. And I'm emphasizing this with a little a min dot here. So the min dot is the number of iterations that minimizes the validation loss. And so this is an important point because we can see that on the right side of the plot, this is what we call an overfit model, because you see there's a very big gap between the subtrain set error and the validation set error. And that's true regardless of what the pattern we're looking at, right? Conversely, on the left, we can see that, the subtrain and the validation error are quite similar. And so this is with a few number of iterations. We haven't really fit very much the subtrain data set at all, so we haven't really got a chance to overfit. But so as we increase the number of iterations, we see that they both go down up to a certain point, but at some point the validation error starts going up, and that's where we start. That's where we say we start overfitting. And so that's bad again, because we're doing worse on some held out test samples, and that's our ultimate goal in the end. So the next thing I want to show is so a little bit more discussion about overfitting. So it happens when the subtrain error decreases but the validation error increases as a function of some hyperparameter. And so here the hyperparameter is the max iterations of the gradient descent learning algorithm. And so, yeah, in the figure that we saw, the overfitting starts after 10 or 100 iterations. So to maximize prediction accuracy, we need to choose a hyperparameter with minimal validation error or loss. And so the optimal hyperparameter will depend on the data set. So In this case, that means choosing 10 iterations for the linear data set and 100 iterations for the quadratic assigned data sets. So this is an important point, you know, the best number of iterations or the best hyperparameter really is not like a universal thing, and we don't know in advance based on the data. We need to do an empirical test like this to find what the best hyperparameters are in every different data set. So here in the first data set, we see that it's 10, which is the best, and in the second two data sets, it seems like 100 is best. But if, you know, we have a more complicated data set, or, you know, maybe it's 1,000 or 10,000, which would be the best. We don't know until we try. So finally, to compute those subtrain validation loss curves in R, you know, basically to resume our previous code block, I mean, what we need to do is we need to assign a new value to a new column to our pattern data data table, and so that's going to, we're going to create a new pred.y column using predict fit pattern. So remember this fit object here, this is the result of the nnet call that we stored earlier. So this is going to store all of the information that we need to make a prediction in R using this learn model. So if we use that on our pattern data object here, we're going to get a new column called pred.y, which is all of the predicted values, and then we can create a new data table, which is a net loss dt list thing. And so here I'm using the paste function to create a new list element name for every combination of pattern and the number of maximum number of iterations. And so in this data table, I'm going to be putting what is the pattern ID, what is the max number of iterations, and then finally here, this is syntax for kind of doing a summarization of the data. And so here, when I use the square brackets, comma, then dot parentheses notation, what it means is that we're going to be computing something using the variables in that data table. And here what we want to compute is this new MSE column. The mean squared error is defined as the mean of the squared difference between the pred.y, the predicted values that we just computed, and the actual labeled y values here that we have in the original data set. And we're doing this, so by equals set, that means we want to do that for both subtrain and validation sets independently of each other. And so at the end of that, we can combine all of those results into this nnet loss dt object, and what that looks like is something like this, where we have one row for every you know, every different value of pattern, every different value of set, every different value of maximum iterations, and it's going to say, and then this final column MSE, this is what we compute here. This is going to be the mean squared error that we've computed for each data set, and, you know, split set, and maximum iteration value. So those are the values that we were plotting on the previous plot here. So if we do the same kind of thing with a neural network with only 2 hidden units, so what does that look like? So here, remember in the previous one we did a test with a neural network with 20 hidden units. So if we decrease the number of hidden units, what does that do? Let's just see what it does, and then after we'll discuss what it actually means. So by decreasing the number of hidden units in the neural network, remember this is a hyperparameter that controls, you know, how much overfitting is happening. So here, what it looks like in the first iteration is something that's not fitting super well. In the second iteration, it looks like, you know, it's again, you know, it's getting a little bit better after 100 iterations. Well, it seems like it's doing pretty well for the linear pattern, and, you know, not so well for the other two. And so same thing, going out to 10,000 iterations, it's not really able to learn something which is doing a good job even on the subtrain set of the quadratic and the sign patterns. It's doing pretty well in the linear pattern case. And so what that looks like in summary is that, here when we're plotting the mean squared error as a function of the max iterations of the gradient descent learning algorithm, what we get in the first case is, the linear, for the linear, quadratic, and sign pattern, we see that the subtrain and the validation, both the subtrain and the validation mean squared error are going down, and we never see the validation error going back up again, essentially. Well, I mean, we see it, I guess, you see the min highlighted at either, 10 or 1,000 iterations here, but you see that it's not really significantly going back up again. So what this implies is that, this model is not really, it doesn't have a very large learning capacity. And actually, we can see that in these figures, right? So it's not able to really approximate this sign pattern very well. It just learns a constant function. And it's not able to learn this quadratic function very well either. So, yeah, I mean, what happens when we decrease the number of units? We decrease the ability of the algorithm to adapt to different patterns in the data, right? So it does pretty well in the linear case, but not in these other non-linear cases. So now I think is a good time to pause and say exactly like what is this neural network doing. So I mean, here I've shown a couple of equations that explain exactly how the neural network makes a prediction. So with a single layer neural network, we in the previous example we just have one input or feature x, which is a real number, and so that's appearing in this first equation here. So for each hidden unit j, we're calling that hj. To compute that value, what we have to do is we first multiply the input by a weight wj, and then we have to add a bias or intercept term bj. And then after that, we take that affine transformation, we put it through this sigmoid activation function, which we have the equation for here. That's just kind of one of the standard activation functions that we use for neural networks. It takes a real number as input and outputs a number between 0 and 1. And so after that, that's the value of the hidden unit. And then after we get the value of the hidden unit, well, we kind of do another affine transformation where with what we're doing is we're taking a linear combination of all of the hidden units weighted by these other weight variables vj, and then we're adding this new bias intercept term beta, and that's how we get our final predicted output. So yeah, in summary, I mean, we have these two equations, but I mean, essentially all that the new neural network is doing is these affine transformations, multiplication and adding, followed by these nonlinear activations, right? So here, the important thing to note about this is that, the things that there's some things that are learned and there's some things that are fixed. So in this case, the activation function is fixed. The sigmoid function is not learned as a function of the data. It's just always assumed to be that way. And however, and the hidden units here, the hj, they're computed as a function of these other things. But so all of these other parameters, w, b, v, and beta, these are all real valued weights which are learned using gradient descent to minimize the squared error. So for example, for one of those problems, and for u equals 2 hidden units, we have the following coefficients, and this is what you get when you type coef fit in R. You get this kind of vector of real valued weights, and so each one of these things correspond to the values of these w, b, v, and beta that we see in these equations up here. So these are the b arrow h1, b arrow h2. These are these bj guys. These I1 arrow h1, I1 arrow h2. These are the wj's that we see in this equation. The B arrow O, this is the beta that we see over here. The H1 arrow O and H2 arrow O, those are the Vj that we see in this equation over here. And yeah, so what's important to note is that these weights will depend on the data, right? So they will be different for those three different patterns that we saw. And the other thing to note is that this number u here u equals 2. This is what we see when there's only 2 hidden units. But if there's 20 or more than that, we're going to see a lot more of these learned weights. So there's going to be a lot more learned parameters that we can fit our data set with. And yeah, and so what the learning actually does is it considers, at iteration, what are the current values of these parameters and what are the resulting predicted values, what is the resulting squared error loss, and then, based on that we compute gradients using the calculus and the chain rule, and we're able to use those gradients to say, okay, well, which direction should I change these parameters in order to get better predictions? So maybe, -40 is not a good value for making good predictions with this guy, but the gradient will tell us, well, you should increase that value and you'll get a better prediction. And so that's what the gradient descent is doing. It's repeatedly computing these gradients, which tell us which direction to change each of these guys in order to get better predictions. So final example is a neural network with 200 hidden units. And so this has got even more hidden units than the previous two examples, which we saw had either 20 or 2 hidden units. And so again, at one gradient descent iteration, it looks pretty much like a flat line like that we're learning. After 10 iterations, we see that we're already fitting the quadratic function pretty well. And the sine, we're doing a little, maybe a little bit under estimation in this area, but doing pretty good. After 100 iterations, we start to see a little bit of overfitting over here for the linear and maybe for the sine pattern. And after 1,000, yeah, overfitting is pretty evident. And then after 10,000, we see that, we're doing a lot of overfitting, right? So it's really big wiggly lines that are going through all of the subtrain data sets, but are not doing a good job on the corresponding validation data points. And so this summary plot looks like, well, the mean squared error is a function of the number of iterations. So here the subtrain goes down, and it keeps going down quite strongly as a function of the number of iterations, whereas the validation error, it starts going down and then it quickly starts going up, right? So we can see that, with respect to the previous two pictures, with 200 hidden units, we see an even bigger gap at the most number of iterations, right? We can see we can fit the subtrain data really, really well, but it's not helping in terms of generalization, in terms of unseen validation data. So, yeah, so just some final comments about this section. I've showed you models of 3 different sizes of hidden units. So the first one we saw was the model with 20 hidden units. The model with 2 hidden units is less flexible. It does not fit the subtrain data as well, and it does not overfit as much. The model with 200 hidden units is more flexible, so it fits the subtrain data even better, and it overfits even more. So therefore, we can conclude that both model size, as measured in the number of hidden units, it's also a hyperparameter that can be used to control overfitting. So that's in addition to the number of iterations, which we already were seeing is another hyperparameter that can be used to control overfitting. So so yeah, a little bit of comment about the R code that you would need to fit these other models, right? So all you have to do is to change size equals 2 or 200 in the previous nnet code that we showed before. Or even better, what I did is I wrote a for loop over size values, and so I encourage you to take a look at my R script to see how I did that. And so finally, the big take-home message of this part of the tutorial is really you definitely always need to have a held out validation set to choose the best values of hyperparameters. So the hyperparameters that we saw here are the number of iterations and the hidden units. For different machine learning algorithms, you'll have different hyperparameters, but in every algorithm there will be something that you need to choose using this held out validation set, because you'll always see these same characteristic error curves with any machine learning algorithm, where the subtrain error is always going down as a function of the hyperparameter, but the validation error is not always going down. So when the validation error starts going up, that's when you start to overfit, and that's not good. It means you're not going to do well when you try to generalize that model to new unseen data points. And so you need to stop or choose the parameter which is just before you start to overfit. And so that's what we're highlighting here with the block dot. So so thanks again for listening, and hope you join me for the last part of the talk, which is a tutorial about image classification.